Evening, everybody. It's 5 o'clock Thursday evening. Time for some Calc 3. All right. So before we jump into LaGrange multipliers, which is actually a pretty cool section, just a couple reminders. We do have the midterm coming up. So make sure you schedule a date to take the midterm. You have up until, I think, the 15th. It's in the Moore calendar. Guys, if you want to take up to that time, that is totally fine. If it's to your advantage to take it a little bit earlier, no problem. All right. So you guys do what is best for your schedule when it comes to scheduling your exam. All the review materials are available. The take-home problems are available. And so make sure that you're taking a look at those. We have 2 more days of content, today and Tuesday. Today we're going to do LaGrange multipliers, which is a nice extension of what we were doing on Tuesday because it has to do with optimization. And next week on Tuesday, we're going to do the chain rule, which is actually not one of the denser topics. This today is. And so what my goal is for today, I want to spend a little bit of time introducing the LaGrange multiplier method, give you an intuitive sense of where the method comes from. We'll do an example together, and then I'm going to have you guys go into groups to do a couple of problems. So I really want to keep my part along the shorter side, if possible, and give you guys more time to work on groups. Because when it comes to LaGrange multipliers, really the biggest part is getting through some of the algebra. And that just takes a little bit of time because you have to solve a system of equations. All right. Just a reminder, a week from today, we won't have anything scheduled. I'll still set up the Zoom meeting like usual, and I'll be here. But basically, it'll be like an extended office hours. So don't feel like you have to be here. Just come, if you have questions or if you want to see what kind of questions other people have, that's fine too. But again, you can always email me questions. You can always ask your questions to the tutors in either the Mass Center on the forum or through BrainFuse. So next Thursday is an open day because we are getting ready for the midterm exam. All right. Okay, so any questions about any of the midterm or any general stuff, take-home problems, let's save those for the end of class because I want to jump into this because, like I said, I want to make sure you guys have good, ample group time. So let's talk about the LaGrange multiplier method. So the LaGrange multiplier method is for what we call constrained optimization, meaning we want to optimize something subject to a constraint. We want to maximize profit with the constraint of a budget. We want to maximize the volume of something with the constraint of the materials that we have available, et cetera, okay? You guys have done constrained optimization problems in Calc 1. In fact, some of the problems you will do in this section with LaGrange multipliers could also be done in a Calc 1 course using substitution, all right? Now, the nice thing about the LaGrange multiplier method, though, is it expands to more than 2 variables even, and it is a more general method, so it can make things a little bit easier to solve. But in reality, some of the problems you will see can actually be solved either way, and so if you want to try both ways just to see, that's fine. But we're going to focus on the LaGrange multiplier method in here. All right, so a lot of different examples of constrained optimization. So let's talk about what this looks like. We're going to look at the situation geometrically because I do want you to just get a sense of why we do what we do. Really choppy? How am I sounding right now, guys? I did get a note that for some reason my internet's a little choppy, sometimes choppy. Okay, what I'm going to do, I don't want to have to do a full reboot of the modem. Let's see if this rectifies itself. For some reason, this is the second or third time it seems to happen around this time. I wonder if it's just the bandwidth of a lot of people getting out of work and getting online. Okay, how's everything right now? Okay. Do me a favor, you guys, and you guys have been great about this. I'll try and keep an eye on chat as well. Let me know if it starts to get choppy or if you need me to repeat anything. What I'll do is I'll slow the pace down a little bit. But like I said, my goal is to get through my part pretty quickly to get you guys working in groups, and then hopefully this will be a non-issue. All right, but keep me posted. So a typical LaGrange multiplier problem will look like this. There may or may not be a context. So suppose we want to minimize a function. So here, x squared plus y squared is our basic paraboloid, subject to the constraint x plus 2y equals 10. The function we're trying to optimize is called the objective function. The other function is called the constraint equation, all right? So a little bit of terminology. One difference I want you to notice that helps us identify which one is the objective function and which one is the constraint. The objective function is a function. In other words, it'll be written as f of xy equals something in terms of x and y. The constraint is actually an equation, which you can see right here, x plus 2y equals 10. Okay, so it involves our two variables, but it's written as an equation instead of as a function. Now, I'm calling it g of xy because of the way we set up our LaGrange multipliers, but typically you wouldn't see this. You would just see optimize f of xy equals x squared plus y squared subject to x plus 2y equals 10. So your constraint will typically be an equation, whereas what we're trying to optimize is a function. Now, it's really cool where LaGrange multipliers comes from. So here's our curve, and what I can do is, in the contour plot settings, I can add a constraint curve. This is something that you guys can do when you go to work problems, so I wanted to show it to you. So add a constraint curve, and click that arrow, and here's your options: no constraint, a function. I do have to solve it for y, but that's okay, it's an equation. Yeah, I know if you want to do it as a circle centered at the origin, an ellipse, or parametric equations, all those will work. This one's going to be fine for us. So our function solved for y would be y equals 5 minus x over 2. All right, so just some linear function. And I should already have this in here. Yep. And let's get it added to our contour plot. Okay.
Why do we want to solve the constraint for y as opposed to just leaving it? Just so we can graph it or put it in the graphing software?
It was the only option they give in the graphing software.
Okay, but we don't actually need to do it for handwritten LaGrange.
Exactly. For LaGrange, actually, we don't, and we won't even bother with it.
Okay, all right, just wondering.
No, it's a good question. It's just a constraint of the software. I'm going to come back to the contour plot in a second, but I want to show you what's going on in the 3D plot. Let me zoom out just a little. What's nice is we can see where the plane cuts through our three-dimensional plot. Why is that getting cut? Oh, let me do this so you can see it even better. There. See that blue line? That's the intersection of our constraint, which is this purple plane, along with our curve. Right there is going to be the minimum value of our function subject to our constraint, because it's the lowest value that is on the intersection of our constraint and our surface. So geometrically, this is the point that we are trying to find, all right? And what LaGrange multiplier method allows us to do is find it algebraically. So I want to reset the contour plot because I want you to see now from the contours, because this is going to be what creates the LaGrange multiplier method. So I'm going to zoom in a little bit here, and actually I've got it on this slide and it might be a little easier to see. This black line is our constraint and we've got our contour plot. Think about what we want to do. We want to optimize our function. So what we want to do is find a level curve that our constraint is tangent to. So keep zooming in here. We can see that there's a level curve right in there where our tangent line is, excuse me, not our tangent line, where our constraint curve is tangent to our level curve, right? It's not going to be this contour. It's going to be the contour just right on top of it that's not plotted. Now, this is the whole idea behind LaGrange multiplier method, because what that means is we want the level curve whose gradient is parallel to the gradient of our constraint. Okay, that is the key to Lagrange multiplier method. I'm going to say it again. We want the level curve whose gradient is parallel to the gradient of our constraint. Why the gradient? Because we know it's going to be perpendicular to both our level curve and our constraint curve. Let's put it on here where we can. All right, so we want, they don't have to be the same length. They could be two different lengths. We might have one that's a little shorter. Let's do that in a little, sorry. Having a technological issue here. You guys still hearing me okay? Lost my plot.
Yep.
Okay. Lost my screen there for a second, and now.
Yeah, I'm a little stuck on what you said, because the gradient in this case is perpendicular to that.
When you say that, what do you mean by that?
What's that? I'm sorry.
You said the gradient is perpendicular to that. What, when you say that, what are you referring to?
Is that the constraint equation, the black line?
Yes.
Okay, yes. So the constraint equation could sound like you said it's always parallel to the gradient?
No. We want the gradient of the constraint to be parallel to the gradient of the level curve. The reason is because both of those will be perpendicular to the tangent line of each.
Got it.
Did that help clear that up?
Yeah.
So here's the key, because it's a little tricky idea, but what we want, you know, let me draw in the level curve that we want. I'm having a little trouble with the 3D plotter at the moment. So we want the level curve that's about right here, that sits nice and tangent, so that there's this point of tangency. Well, to do that, what we need is we need their gradients to be parallel, because we know those will both be perpendicular to the level curve at that point and to the constraint at that point. All right. Now that's the whole idea behind it. That's not something you need to memorize, but I wanted to give you an intuitive sense of where the method comes from, because then what we do is we think of our constraint as a function, and then we need its gradient to be parallel to the gradient of our original function. And again, we only need them to be parallel. We don't need them to be equal. And that's why we put this lambda in there, right here. Because when two vectors are parallel, they're a scalar multiple of each other. So that's what we need to have happen. And what it does is that's what sets up our system of equations that we solved that you saw in the lesson videos. We can technically put lambda on either side, but we're always going to put it on the side of our constraint equation, because one thing I'm going to show you after we do an example is lambda has a very particular interpretation in terms of an instantaneous rate of change. All right. This here is the LaGrange multiplier method. So in general, what this looks like is we need to match up their partials, and then we have our constraint equation. Now, let's go to let's do an example together so you guys can see this kind of play out. It's a nice example to get us kind of introduced. And again, this generalizes to more than two variables, generalizes to more complicated functions. So I had given you f of xy equals x squared plus y squared, and the constraint was x plus 2y equals 10. So what we do is we say, okay, well, we're going to let g of xy, g of xy equal x plus 2y. And so we're doing this subject to the constraint g of xy equals 10. All right. So this will be our system, and it's going to be a 3x3 system because we're going to have three variables. X, y, and lambda is our three variables, and we have three equations. So here's how we do this. First thing we do is we calculate f of x, partial with respect to x, which is 2x, f sub y, which is our partial with respect to y, which is 2y, and we do the same thing for g. G of x, partial with respect to x, is 1, partial with respect to y is 2. Now we set up our system. So you're going to start off by taking the partials of your function and then taking the partials of your constraint equation. Now here's where the 3x3 system comes in. We're going to have f sub x, so 2x equals lambda times g sub x, so lambda times 1. F sub y equals 2y, lambda times g sub y times 2, and then our constraint equation equal to 10. So x plus 2y equals 10. That is our 3x3 system. We have three variables, x, y, and lambda, and three equations. Questions about where, oh, yeah.
It's like the choppiness is getting pretty bad.
Okay.
Like I understand what you were saying, but it's like it's getting pretty bad.
Okay.
Yeah.
Yeah, something's up with the internet here for some reason, and I don't know why. Okay.
All right.
Are you guys able to see what I'm writing?
Yeah.
Yes. The question came up, is C just the constant 10? Yes. The C here is what our constraint equation is set equal to. In our case, that'd be the 10. Okay. I'm going to keep on going. I'll slow down. Yes, you'll always have one side as a constant because the other side will be your variables. You can always set the constant to one side and your variables to the other. So that'll always be a constant because we can isolate the constant. Let me know if you guys need anything repeated. I'm happy to repeat it. And I apologize for the cutting out. Other questions about setting up the system here? Again, all I'm doing is taking the partials of my objective function, setting them equal to lambda times my constraint, the partials of my constraint, and then the actual constraint. Now, once you set up the system, the rest is all algebra. The reason I really want to emphasize this, what we've done up till now involves stuff that we just learned. Partial derivatives, and what we just now talked about introducing this lambda because we need parallel vectors. But going forward from here on out, the rest is just algebra. Now, that doesn't mean the algebra will be easy. It's going to depend on the problem. This algebra can get really nasty, or the algebra might be very simple. But I just want you to realize that from here on out, all I'm doing is algebra to solve for x, y, and lambda. And that if you get one with messy algebra, computer algebra systems like Wolfram Alpha, Maple, Mathematica, things like that, are very good at solving systems of equations, okay? So here's one way of solving this. Guys, solving systems of equations, there's a bunch of ways. You have things like elimination, substitution. What you decide to sub for may change from problem to problem. So I'm going to show you how I would solve this one, but that doesn't mean it's going to be the best way for all problems. And that's why I wanted to emphasize that going from here on out, it's algebra. The way that we solve this one may not be the best way you solve one of the ones in the homework or one of the ones from the worksheet. You might find an easier way. But what I would recognize here is I can solve this first one for x, and I get x equals, let me know if I'm cutting out.
Wait, what did you say? You said what I recognize here is, and then it just totally died.
Yeah. What I recognize here is I can solve this first equation for x.
I did it again, like I'm literally in the same part.
Yeah. What I recognize here is I can solve this first equation for x in terms of lambda.
Got it.
So, and just keep letting me know.
All right. I'll just keep my mic on and tell you.
That's fine. X equals lambda over 2. All right, so I'm solving the first equation for x in terms of lambda, and I can solve the second equation for y in terms of lambda, and I get y equals lambda. Divide both sides by 2. The reason I'm doing that for this particular one is I can plug those in for the x and y here, and I get lambda over 2 plus 2 times lambda equals 10. And I get something I can solve for lambda. All right. Adding those together, I'm going to get 5/2 lambda equals 10, or that lambda equals 4. So I'm kind of ran myself out of space here. And again, let me know if I cut out. I'm happy to repeat anything. Now I can go and back solve. Because if lambda is 4, then x is 4.
Now you can do what?
So now that I know lambda equals 4, I can go back solve and plug this lambda value 4 in for my lambdas.
Okay.
So that gives me x equals 2. And that gives me y equals 4. So what this tells me is that the optimal value and what's going to minimize this function with subject to our constraint is going to happen at the point 2, 4 with a lambda of 4. And now to get the minimum value, I'm going to plug it into our function. F of 2, 4, which is 2 squared plus 4 squared, which is 20. And if we go back to our curve, if we look right up there at 20, we see that that's looks to be very accurate. And if we go back to the contour plot, it's moving a little slow today. We see that that point where their tangent is roughly where X is 2 and Y is 4. So graphically, it seems to match up with what we found. So we found that the minimum is 20, and that occurs when X is 2 and Y is 4. All right. Questions about that? About how we solve that? Now again, that's not the minimum of our function. That's the minimum of our function subject to this constraint. Okay. One last thing I want to talk to you about, and then I'll get you guys into groups so you can try a couple. Now, as I mentioned, lambda is called the LaGrange multiplier. I want to talk specifically about the interpretation of lambda because it's very interesting and it has a lot to do with related rates. All right. Now, one thing I'll mention, if g of x, if the constraint is bounded and closed, then we're guaranteed both a global min and a global max. This constraint is not bounded. It's closed but not bounded, and we could see that from the graph. Back to 3D. If I can get this down a little bit, see how it shoots up to, whoops, too much. See how it shoots up to positive infinity? There's no maximum subject to this constraint because our constraint was not closed and bounded. An example of a closed bounded constraint would be like if you have a circle or an ellipse. Those are closed and bounded. You would be guaranteed both a max and a min. Very similar to the one that we looked at on Tuesday. All right. Now, this part I want to talk to you about. I'm going to gloss over the derivation because it involves the chain rule. Because the way I used to do the material, I used to do the chain rule first and then LaGrange multipliers. But because we're not going to do the chain rule until Tuesday, I don't want to bog you down with that part. We'll come back and look at this after we look at the chain rule on Tuesday. But what we can do is, the way we derive this is we think of our optimal point, the 2, 4. We think of them as functions of our constraint or our C value here. This is our C. Think of this as a budget. Say we want to minimize, what do we want to, I want to think of do something kind of interesting here. Say we want to minimize surface area with constraint to our budget, and our budget is $10 and our surface area is being measured in square feet. Okay, so this guy here is in square feet. This guy here is in dollars. Well, every time I change my budget, the point that produces my optimal value will change as well. So what we're doing is we're thinking of these values as our x0 and y0 as implicit functions of C, okay? Meaning that if we change C, x0 and y0 will change in a corresponding way. All right. Now, what that allows us to do, and again, this is going to be a chain rule thing, so I don't want you to worry too much about this next slide. We'll come back to it on Tuesday. But when we look at the change of Z0, which is our optimal value, that would be the 20 in this case. So basically what we found is for a $10 budget, the minimum surface area would be 20 square feet. After we do the chain rule, what we find is that after doing all this work, lambda is equal to dz0 dc. Here's why this is so important and so cool. Think about what this notation means. This means a change in our optimal value with respect to a change in our constraint. And this is an instantaneous rate of change. That means that what lambda gives us is the instantaneous rate of change in our optimal value with respect to change in our constraint. So one way we can use that is to predict what our optimal value would change by for an increase or decrease in our constraint. What do I mean by that? Let's go to our example here where we have some numbers to work with. Let's say we're able to increase our budget by $1. So we increase C to $11. So that's an increase of $1. We would expect our optimal value to increase by about lambda. So we did have 20 square feet. Lambda's positive. We would expect the optimal value to go up by about by about 4 square feet. So approximately the new optimal value would be 24 square feet. All right. Now, this is something I want you to try and get used to, and it's something you'll get asked in the homework as well. But we're going to do. I'm going to give you a LaGrange multiplier problem in a context. So what I'm going to ask you to do is give the units on your LaGrange multiplier. So that 4. Well, it's dz0. Well, z, our function, our optimal value was measured in feet squared. And our constraint was measured in dollars. So what our lambda means is that at the optimal point of 2,4, our square footage is going up by about 4 square feet per dollar increase in budget. Questions about that? Hopefully you guys are still able to hear me. Is the audio still coming through okay?
Yep.
Okay. So questions about that interpretation of the LaGrange multiplier?
It's in the constraint, right? Based on the C is a constraint based on. Yep. Sorry. So
Go ahead.
Lambda is a change per unit of increase in C, per unit of increase in the constant of our constraint, which is 10 in that case.
Yes.
Okay, thanks.
Yeah, guys, and it's why it's so powerful. I don't need to rework my entire LaGrange multiplier problem. So think about this in a practical setting, right? Somebody comes to you and says, hey, we just found a way to increase our budget by X amount of dollars. How much more square footage, or how much more profit, or how much less cost, or whatever it is we're trying to optimize can we get? Well, because we have the LaGrange multiplier, we can give an estimate. Now, just like in Calc 1, the LaGrange multiplier is an instantaneous rate of change. So it's a good estimate locally. So for small changes in our constraint, so if we, in this case, our C went up by 1. Now, if you start saying, okay, well, what if we double our C? Like if we go from 10 to 20, it's not going to be as accurate because it's an instantaneous rate of change. And that would be a case where we would probably just recalculate the whole problem. But for a very small increase in our constraint, it gives us an approximate change in our optimal value. And so what I'm going to ask you guys to do today, so every group is going to get a straightforward problem with no context, and every group's going to get a problem that is in a context. For the problem in a context, all I want you to do for today is give the units on your LaGrange multiplier and maybe think of what it means in a sentence. In other words, if and this is something you had to do, I'm sure, a bunch of times in Calc 1. So what I would say here, my Lagrange multiplier is 4. So what does that mean? Well, that means, you know, when my constraint is $10, my optimal value is increasing by about 4 square feet per dollar at that constraint level, at the constraint of $10. I kind of said that twice, but for this problem, our optimal value is increasing by 4 square feet per dollar when our constraint is $10. All right. So that's just something I want you to practice today, because it's something it's a question you're gonna have in the homework, and it is a question you're gonna get on the midterm, which is, you know, interpret what is the meaning of the Lagrange multiplier, or what are the units on the Lagrange multiplier. All right. So I want you to practice that today. All right, guys, questions at this point? Okay, so I just put the worksheet in chat, and let's see. I think we'll do just, okay, let me get you guys into groups then. Hey guys, so we're running down on time. It's about, we only got a few minutes left, and I wanted to have an opportunity to say just a couple things before we hit 6:30. So first off, for posting on the forum, you only have to post 1A. Now, if you want to post number 2 or number 3 because you decided to work on it, by all means, go ahead and post it. I'll definitely give you credit for it, but just don't feel like you have to, because I know we didn't have quite enough time to really get to 2 or 3, because they do take a little bit longer. As you guys are preparing for the midterm, number 5 is a good Lagrange multiplier problem. It's one that I used to give on past exams. Obviously, I don't give it anymore. But if you wanted to start to get an idea of what the level of an exam problem might feel like, number 5 is a really good one. And as always, guys, you get the answer key on the worksheet, and you have the solutions in course content. All right. So you can always check your work. All right. I want to just mention a couple other things about the exam. As we mentioned at the beginning of class, next week we have one section left on Tuesday, which is the chain rule. I'm going to try and give a little bit of time at the end of class to talk about the midterm and take some questions. But then Thursday is an open day. Come in if you have questions, but if you don't, if you want to work on take-home problems, or you want to just study for the midterm on your own or in groups, totally fine. As always, guys, I encourage you guys to work together outside of class, studying for the midterm. You guys are all taking the same exam, so feel free to meet on things like Google Meet, Zoom, Skype. If you guys are comfortable meeting in person, obviously that is fine too. So, take advantage of each other as a resource. If you're having trouble, you can always post in the forum if you want to try and create a group. Or if you want, some people in some of my other classes have started a Discord chat. If you need any help with me emailing out some of that information, I'm totally fine with that. The other thing, there is the midterm review folder in course content. If you haven't done so already, maybe this weekend, make sure you check that out to start seeing what you have questions about. There is a review of more problems in that folder. Those are good review problems, but it is not comprehensive, meaning there will be some problems on the midterm that are going to be exactly like those more problems. And then there'll be some problems on the midterm that are going to be a little bit different, to just make sure that you understand the material. So going through things like the worksheets are going to be a good way of getting a little bit of extra practice. Okay. All right, so I wanted to have a little bit of time to mention that at the end. We're actually a minute over, as usual. Apologies for the sound issue this morning, or earlier in class. I guess that wasn't this morning. I'm going to see what I can do to see if I can get that to stop happening. Yeah, if you guys don't have any questions, we are done for tonight. Like I said, we have one section left before the midterm. It is a shorter section by comparison to the last couple of sections. A little bit lighter, I think. You know, we're trying to lighten up so you guys do have more time to study, focus on the take-home problems, and get that stuff done. But let me know if you have any questions. I can hang around for a few minutes and answer what I can answer. If you guys are good, then I will see you on Tuesday. And as always, remember, you can email me over the weekend. You can post on the forum. There is tutoring through the Math Center over the weekend. And you always have tutoring on Brain Fuse if you're outside the Math Center hours. Okay, so please take advantage of all of those. All those resources are completely free for you guys to use. And also take advantage of each other as a resource, you know, communicate, work on homework problems together by all means, okay? Have a good night, guys. Like I said, if you have any questions, fire away. No problem, Andre. Have a good night.